Hello, everyone. Good morning, good afternoon, good evening, from whichever part of the world you're connecting from. My name is Bukola Orunti, and I'm the instructor for this course, Network Operations 1.0. Last week, we looked at the Module 1 of the course, and we covered the following topics: Introduction to Unix and Introductions to FreeBSD. So this week, we'll be looking at the Module 2, Networking Overview, and the first topic we'll be treating today is network layers and IP addressing. The objective for this second module, that is this topic, is to describe the TCP and OSI models used for network layering, and also to explain the characteristics and differences between IPv4 and IPv6. Networking concepts. Now, the internet is the largest network of computers that exists. It is a network of networks. Just like we like to say, different networks coming together to form a single overall large network is known as the internet. Now, managing data communication within such a web of interconnected machines is such a complex task, if you want to agree with me. And also, network layering then provides a reliable way of dealing with complex data exchanges and communications within and across networks. So in networking, the word layering simply means to break up the sending of messages or sending of data into separate components and activities. Each component handles different parts of the communication. So two models that are being used or that have been widely referenced are the OSI and the TCP/IP. The concepts are similar, but the layers themselves actually differs between these two models. So here is the two models put side by side graphically. We can see in the OSI model, it has 7 layers, and the TCP/IP model has 4 layers. Now we'll start with the OSI model. And the OSI model was developed by the International Organization for Standardization. There are 7 layers in the OSI model, just as we can see on our screen. I will start from the topmost layer, as we can see here, which is known as the 7th layer, which is the application layer. This is the layer that is nearest to the end users, and it is the layer where application protocols are represented. Examples of protocols that we're looking at here is the HTTP or HTTPS. Otherwise, this is the protocol used by web browser applications. So for any user, for example, you need to visit a website, you just click on your browser, and then you believe it takes you there. So at that instance, the protocol you're interacting with is the HTTP or the HTTPS protocol. Now, the next layer directly underneath, which is known as the 6th layer, is the presentation layer. This layer receives application data from the 7th layer and then encrypts or converts it to binary data as it leaves your network. So actually, the presentation layer is the layer where encryption is done before any data leaves the network. Now, directly beneath this presentation layer is a 5th layer, otherwise known as the session layer. This layer controls the dialogues, that is the connections between computers. It establishes, manages, and terminates connections between the local and remote application. So this layer is actually the one that opens and closes sessions between two different applications or two remote applications or two different systems, one local, one remote. Then the 4th layer underneath the session layer is known as a transport layer. This is the layer where the well-known protocols such as protocol, which are the TCP and the UDP. This is the layer where they exist. Now, what is the difference? The TCP, that's Transport Control Protocol, it favors data quality over speed, while the UDP favors speed over data quality. So for TCP, TCP guarantees delivery. That is, it uses a three-way handshake to ensure proper connection between sender and receiver is established before the transmission of data, and also it confirms or verifies from sender to receiver to ensure that the data that was sent and received are actually correct, or they were correctly received just as the sender intends it. While the UDP is known as connectionless or unreliable, it doesn't care. Once it connects to a receiver, it just sends, and it doesn't go back to verify whether they actually accurately sent, was it sent to the right medium. It just sends its own data. That's why it's referred to as connectionless and unreliable. In TCP, it's used in email sending, in web communications, where UDP is used in video and audio streams. Now the third layer, that is the layer directly under transport, is the network layer. This is the layer where routing occurs. We look more into routing later, later in this course. Now the layer provides a means of transferring datagrams from one node to another using routers or routers. Routers have routing tables and forwarding tables within them. Now, it determines the best path available to reach a specified host, and it selects from the routing table the path to use. And then once it selects a particular path, then it installs that information in the forwarding table. It's as simple as that. So the next layer is the data link layer, otherwise known as the second layer. The data link, this layer receives packet from the network layer. It performs physical addressing, that is, it adds the sender and the receiver's MAC address, that is their media access control address, to the data packet to form what is referred to as a frame. When it collects the unique identity, which is the MAC address of the sender, and then that's of the sending device, and then the receiving device, it adds these two information to the data that is going out. And then at the end of the day, this more compounded data is known as the frame. So that when it gets to where it's going, it has the information where it's coming from, and then it helps to assure it gets to the correct interface or the correct machine. Now the last one, and which is the last list under this, directly under the data link layer, is the physical layer, which is known as the first layer. The physical layer, this is the layer that defines the physical transmission media over which signaling occurs. So the physical media here, examples are wires of all types, the cable, the fiber optics, the copper cable, and the likes. And the equipment that are usually used as the physical layer, example, the hub, the repeaters. So it's the physical medium through which data is transferred from one local device to a remote device. Now that completes the OSI model. OSI model, it has 7 layers. Now the second model also used is the TCP/IP model. The TCP/IP is a set of communication protocols that define how different types of computers talk to each other. The two protocols in use are TCP Transmission Control Protocol and the Internet Protocol. This model has 4 functional layers. The first, or the fourth now, The fourth layer, just like the OSI was considered from the seventh to the fourth, this one is also being looked at from the fourth to the fourth. So the fourth layer is the application layer. It consists of protocols to allow applications to access the services of other layers. Like we also said in TCP/IP, examples of protocols being used here is the HTTP, the Hypertext Transfer Protocol. Another one is the FTP, the File Transfer Protocols. So like we said, this is the closest layer to the end user. Now the next one directly under it is the transport layer, which is also known as the layer 3 for TCP/IP model. The transport, this is the layer that provides application layer with session and communication services using TCP and UDP as needed. Then the second layer is the network directly under the transport layer, the network layer. This is the layer that addresses host and packet routing between networks using protocols such as the IP and also ARP. ARP is otherwise known as the Address Resolution Protocol. This is a protocol that connects IP address to a MAC address in local area network. So once it has the information about the IP address, it connects it to the corresponding MAC address. Then the layer 1, which is the last one being looked at here under the TCP/IP model, is the physical. This is the layer responsible for placing packets into and receiving packets from the network. So it places packets in a network and it receives packets from a network. Now we'll be looking at another subtopic under this, which is the IP addressing. In IP addressing, we have two major IP addressing systems in networking. The first one is the IPv4, which has been in existence from inception, and the revised version of it is now the IPv6, IP version 6, IP version 4. Now, IP version 4, an IP address actually, generally considering the two now, an IP address is a numerical label that is assigned to each device participating in a computer network that uses IP for communication. So IP address serves two major functions. The first one is for host or network interface identification, and the second major function of IP addresses is for location addressing. Now let's look at IPv4. IPv4 is a 32-bit addressing type, also known as a 4-octet number in binary. That is, 1 octet stands for 8 bits. So in IPv4, we have 4 octets, each octet separated by dots. So you can read more about it in the RFC 5737 to know everything about IPv4 addressing system, for both IPv4 and IPv6. And in IPv4 addressing system, it has two major parts. One part looks at the network, and the second part looks at the host. So like you can see it here, this is an example of an IPv4 address. And if you look at it, the first layer, it is broken into four parts. That is, 192 is an octet, 0, this next one, 0 is another octet, the next one, 2 is another octet, and the last part, 1 is another octet. And this break is, imagine having it as dots, is separated by dots. So looking at this addressing, particular IPv4 address, the first 3 octets identifies the network part, and the last one octet identifies the host part. And now, how do we know which part is for the network, which part is for the we deduce this from the subnet marks following it. So for this, oh, 255, 255, 255, that's the first three octets that helps us to identify the network path. All the bits are turned to 1. So because all the bits are turned to 1, there's no modification we can do to it. It identifies the network from which the address is coming from. And then the last part, turned 0, help us to identify the host part. If you look at it, the only part that can be shared or whatever is the host part. The network part is the constant part that you cannot mess with. It helps identify the network. So under the IPv4 addresses is 32-bit, and the maximum total number of available IP addresses under it is this, I think, 4 billion addresses. And because it is not enough for our world today, it has been exhausted in virtually everywhere in the world. We have limited number of IPv4 addresses, which is not enough looking at number of devices that we are connecting to the internet today. Thus the need for a review. And then this brought about the IPv6. IPv4, like we said earlier, is a 32-bit address, and IPv6 is 128-bit. And now we have more than enough address for everyone around the world today. So we have available 5 ways per 28 addresses per person. And IPv6 is represented in hexadecimal separated by colon. So this is a typical IPv6 address representation. As you can see here, each octet is separated by, each 16-bit is separated by colon. Not 8-bit now, 16-bit separated by colon, hexadecimal in numbers and in letters. So this is a typical way to write an IPv6 address. We look at it here. In whichever 16-bit part that we have, it's all zeros. So writing the 4 zeros out can represent it as a single 0. And then if 2 zeros are beside each other, then double column lets you know that we have 2 16-bit zeros. 2 octets here in each. So now let's look at the body in charge of IP allocation that makes it go around the world. Now we have the governing body managing IP addresses, which is known as the Internet Assigned Numbers Authority, IANA. Now, an IANA function is actually being managed by another organization known as ICANN, Internet Corporation of Assigned Names and Numbers. They are the one that are managing the functions of the organization known as IANA now. So IANA actually is the one that allocates IP addresses, be it IPv4 or IPv6, to the different continents of the world, to different organizations, to different people. So if you need an IP address as an individual, you don't reach out to IANA by yourself. What you do is, maybe through your ISP, the ISP reaches out to the organization, the registry known as RIR, the regional internet registry that handles IP addresses for your continent. So if you look at it in this image on your screen, you can see that we have 5 of them. One ARIN, we have LACNIC for Latin and Caribbean. We have the ARIN for the American registry. We have the AFRINIC for Africa. And we have APNIC for Asia Pacific, and we have RIPE, I think that covers Europe. So these are the 5 regions that handles the allocation of IP addresses, and they get their block from ICANN that manages their INA functions now. They get it from ICANN, and then from there, they now distribute to interested ISPs within their continent, for IP addresses to be used within their continent. So for the purpose of this class, we'll be looking at the African region, which is the same way it operates in every other region actually. So the IANA, for example, allocates like 12 prefix for the African region for distribution among its the organizations or the citizens within the African region. So the Afrinic then allocates, for example, we are using examples there, now allocate based on request now, maybe the maximum of 32 prefix to an ISP within its region. Now this simply means that a million, 1,048, 1,048,576 IP address was given to a particular ISP within the region. And then they also give the likes of like 32 prefix. They were given IPv6 address was given to the African region, of which is like 32. So by the time they get that, they give now to a particular ISP within their region. So once they get that IP address now, it is not the responsibility of the ISP now to not distribute now to its end users or to any organization that requests IP addresses. So it's like more like division of labor from IANA. Afrinic get a /32 prefix, a /12 prefix. Now Afrinic now allocates based on an ISP's request, but I think the maximum they can give any ISP is /32, and then it comes down and down and then as an individual or as an organization within the coverage of a particular ISP. Now, once you make your request, they also give you based on your request or based on the requirements you have given that you need so number of IP they allocated, but then there's a peg to the maximum that can be given to a single ISP. And then more information about the policies that guide the allocation of IP within the African region can be found on the following links, both for Afrinic and then the IANA's allocation guidelines can also be found on the next URL on your screen. Then, like I was saying earlier, an ISP that got a particular allocation from Afrinic now can give to each end user based on need. So I think the maximum is /48, and then you look at it, which of course is actually based on the request of the customer or the organization. So this is an example of a breakdown of how this allocation goes. This is just an example. It's not strictly the exact that you can get from them. So from IANA, Afrinic at the registry, regional registry receives /12. An ISP receives /32 from Afrinic. An organization receives /48 from an ISP, and then maybe the unit or the ESS subunit within an organization now receives /64. based on its own LAN. Now, what are the key takeaways from this particular networking concept that we have looked at? One, we have understood that network layering provides a reliable way to deal with complex data exchanges and communications within and across networks. Also, we have learned about in networking what layering means, which is to break up the sending of messages into separate components and activities. Also, we have looked at the two models that are widely referenced today, which are the OSI and the TCP/IP. The OSI model has 7 layers, where the TCP/IP has just 4 layers. Also, we have learned about the Internet Protocol address, which is a numerical label assigned to each device. For example, your mobile phone, your computer, your printer, your fax machine, even your smart TV, which are participating in a computer network that uses the Internet Protocol for communication. Also, there are 2 versions of Internet Protocol address, which are IPv4 and IPv6. IPv4 uses a 32-bit address for its internet addresses, while IPv6 utilizes the 128-bit internet addresses. So that concludes Unit 1, which is the first part of our Module 2 course. So, I want to look at the second module. So let me try and share my screen again while we run through the second one. For this module 2, the second topic under module 2. I hope you all can see my screen again. So the second topic we'll be looking at, still under networking overview, we'll be looking at network mask. So under this topic will be the objectives. We are considering how to explain the purpose of network mask, also to work with network mask to create subnets and supernets, and also to determine the number of hosts on a network using network mask. Now, network mask. Network mask is also known as subnet mask. So at times this could be used interchangeably, but they're referring to the same thing. Subnet mask now is, or network mask is a number that defines a range of IP addresses that is available within a network. So like I said earlier when I was introducing IPv4, how it looks numerically, they said there's a part of it that identifies the network and there's another part that identifies the host. Now, based on the network mask, it helps us to know, okay, which group of octets handles the network path, which is you can't change, you can't do anything to it. It just helps to identify, okay, it's from this particular network. And which part now help us know it's for this a particular machine within that network, which is known as the host. So systems within the same subnet can communicate directly with each other, while systems on different subnets, that is from different networks, can communicate only via a device or equipment known as a router. So network mask or subnet mask helps define which bits in the IP addresses are used to describe the network path and also which bit is used to describe the host. So this is an example, like we said. We look at this now. It helps us to generally looking at a 32-bit IPv4 addressing system. And then if you look at this image, it tells us to know, okay, this part is for the network. And if we look at the image before us, all the parts that are turned to ones simply means it is to identify the network. You can't do anything to it. It only tells us, okay, this IP address is from this particular network. This IP, it like helps us to know, okay, we are from the same family, we are from the same group, we are from the same network. So, and the other partner identified, oh, okay, I am Mr. A within this group, I am Mr. B within this group, but we all have the same group identity, which is not the same network identity. So now representing network mask. Now, within a particular LAN, we have host A, host 1, host 2, host 3. Now, we can now know that, okay, because of this network part, it tells us now host 1, 2, and 3 are from within the same LAN, the same network. Now, to now know who is host 3, who is host 2, the host part now gives each of them a unique identity. So they can all get the identity from the pool of available IPs from this host part. So in every network or using any network address, there's always a reserved group of IP address. Even for example, we say, looking at the previous example, 192.0.2.0/17. It means within this /17 network group, yes, group of network addresses, 2 are reserved magically from it. The .0, the first IP in that available group of IP identifies the network, and the last one identifies the broadcast. So when you're talking about available use group of IP addresses, for example, to know the available IP addresses within a particular network, we have, this is an example. This 8 helps us to know, okay, this is the host. So 2 raised to the power 8, 256 IP addresses is available within this network address. And now we have 256 addresses. Now out of it, can we use the whole of these 256, allocate IP addresses to 256 hosts for that particular LAN? No, you have to remove 2. Why? The first IP there is for the network, and the last one is for broadcast. So that is the reason why the next -2 is coming in. So available IP address to allocate to host within these 256 IP addresses simply means we have 254. So the 2 that we removed, one is for the network address, one is for the broadcast. So this is another example. We have a /27, and now that is 2 raised to the power 5 -2. So that is 32 -2. We have available IP addresses to be allocated to hosts within that network of /27 simply means we only have 30 available IP addresses for use. So still looking at the network address and the broadcast address. These are the special IP addresses in every network that you cannot give out. So the subnetting, how can we break IP addresses? Now this is an example. We have an IP addresses, we are given allocated an IP address of /24. And then we want to kind of separate the network. For example, our organization received a /24 IP address. And now we have, maybe in that organization, we have 2 units in that organization. We have the HR, and probably we have the manufacturing unit. And now we want each of them to be on separate networks such that HR people are minding their business, they are sharing files locally without restriction. And then manufacturing organizations, so they are minding their business, they're sharing their own files. And we don't want this information to fly within the 2 networks without authorization. Or fly which are by error or whatever. The best thing to do is to break that slash 24 into two, the IP into two different networks, such that when you send an information from your host A to a B, you have no fear of it getting to human resource or getting to manufacturing. So that's where we do what. That's an example when we can do subnetting. You break a slash 24 into two slash 25. So slash human resource has a slash 25 for its own group of hosts, and manufacturing has slash 25 for its own. So when the information is being shared between the hosts, the fear of it crossing is not there, because probably you don't have a router in between them, or even if you have a router, you are defining strictly instructions within the router so that it doesn't fly. So that's an example of when you can subnet. But there are various reasons for subnetting, but the point is we want to separate a big chunk into smaller chunks of IP addresses. So if I want to break a slash 24 into 2 slash 25, that means for the first slash 25, I have from 0 to 127, and then from 128 for the next one to 255. Also remember that the first IP address 192.0.2.0 is the network, 192.0.2.127 is a broadcast. So you can't allocate these two IP addresses to anyone, or you can allocate every other number in between these two to host. And the same goes for the next one. 128 is a network, .255 is a broadcast. So in between, you can allocate the available IP addresses to the host within that group. So now we have an example here for supernetting. Okay, can we match these two groups into a single slash 24? It simply means no, because one is slash 24, one is slash 23. They are from two different subnets. You can match them to a single one to form a single slash. If it is two slash 25 slash 25, then they can come to become they can demerge to become a single slash 24. Now, why do we do supernetting? At least we understand why we can do subnetting, breaking down. Why do we merge? And the process of aggregating multiple subnets into one, that is summarizing network routes and streamlining network traffic from one network node to another, is known as supernetting. So why do we do supernetting? Besides solving problems associated with IP address shortages, minimizing the routing table and enhancing efficiency is another reason. And it performs route summarization by using the classless interdomain routing, which is known as the CIDR. So route summarization can help reduce memory requirements for every device. Remember we said a router has a forwarding and a routing table and a forwarding table. Now, if the routing table is very large based on number of available IP addresses, it chunks up memory space. So, and it chunks bandwidth. So to avoid that, we use supernetting. We use supernetting. So we said it helps to reduce memory requirements, bandwidth requirements, routing tables, and it provides more network stability for the organization. So how does supernetting work? Actually, the process of supernetting works by following two protocols: the CIDR, the classless interdomain routing, and the EIGRP, the enhanced interior gateway routing protocol. We can read more about this. We can read more about this online. And so as the number of subnets increases, routing table entries also increase. Thus, it causes router overloads on your network. So this challenge can be overcome by combining multiple subnets into one supernet and classless routing of data packets between network nodes. And like I said earlier, supernetting can only be possible between the networks if the networks are contiguous. That is, every network bit is the same, and only the subnet bit is different. So a /24 plus another /24, merging them gives you a single /23 and not the other way around. So if you want to add this 192.18.4.0/24 and 192.18.5.0/24, you can merge them to give us 192.18.4.0/23. So now what are the key takeaways from this networking concept that we have looked at? The network mask. One, a network mask, also referred to as a subnet mask, is a number that defines a range of IP addresses that is available within a network. Network mask or subnet masks help define which bits of the IP addresses are used to describe the network part and which bits are used to describe the host part. So a network mask is similar in appearance to an IP address. Also, there are two special IP addresses, namely the network and the broadcast address. Like we said, the network address represents the IP in a subnet, and it is used to identify the beginning of a network. But that particular IP, you cannot use it and you cannot assign it to a host. And the broadcast address represents the IP address in a subnet also. It is used for sending message to all hosts or nodes in a network. It is also unusable. You cannot assign it to a particular host. So network can be broken down to subnet or merged together to form supernet. So that concludes the second unit of the topic. And then we go to the last part, which is routing under this module 2. So I want to share my screen. Okay, I believe you can all see my screen. Routing. So under the networking overview, we are looking at the third topic here, routing. Now, what are the objectives? One, we have to learn we have to explain how the routing works. So we have to understand how routing actually works in a network. Also to describe the elements in a routing table. Also, we are going to define network routes to each local and external network, and also explain how the Unix Linux operating system can function as a gateway. Now, routing. Routing simply is a word used for the activity that occurs at the network layer of the OSI reference model, which I looked at earlier. And in TCP/IP, routing involves delivering packets to destination IP addresses to machines in other networks. So we can look at it, this routing with the device in between them is a router, and then we have network A, network B, network C. So within network A, host A is trying to send data to host A in network B. So that means because they're in two different networks and they have two different IP addresses, network addresses. So they need a router to help them know where to go and how to get there. So that is the work of the router in between them. Now, the routing concept. The initial mechanism of the routing process consists of determining the path over which packet will travel from the host, that is the sender, to the destination, which in this case would be the receiver host. Now, the second part of the process also involves having routers switch packets from one segment or from one hop or from one router to the next until they arrive at their destination. So in this case, you might need to go through 1, 2, 3, 4, 5, or as many routers as needed for you to get to your desired host. But the key thing here is that each router must know where to send what so that it can get to the desired host. Now, a routing protocol is a protocol that is used for identifying or announcing the network path. So in this case, what is a protocol? Protocol is just a standardized way of formatting data so that any computer connected can understand the data being transferred. So this is an example of the blue network and the purple network now. So host A, maybe server A or machine A needs to send, or machine 1 now, need to send an information to machine 2 in the purple network. So the first router here is directly connected to the blue network. So what it does is, okay, is aware the information, because it is not needed within the blue network, is needed to an address that is out, not available within the blue network. So it simply just sends the information to the router. And the router will now look at, okay, the network address, the sender's network address, the sender's MAC address, and the supposed destination IP address and MAC address that's available within the information. So once it looks at it, is not within its local, then it just send it out to the available addresses that is yes, the available IP addresses within its routing table. When it looks at it, if it's within the routing table, it just sends it to the correct interface and it gets to the network. If it's not, then once it checks the routing table, there will be another address known as the interface known as the gateway that has an address that is universal. You send it out through that. And then that is how it keeps going until it gets to its desired network. Now, routing protocols. We have two, we have two types of routing protocol. The first one is internet protocol, and the second one is border gateway protocol. The internet protocol, which is also known as the IP protocol, it specifies the origin and destination for each data packet. So it identifies the sender IP address and the receiver's IP address. So for each, routers inspect each IP header to identify where to set them, like I also said earlier. And then the other one, known as the border gateway protocol, is a routing protocol that is used to announce which networks control which IP address. So the BGP protocol simply says, okay, this IP address, this is a network that has it. So that information will be available within the border gateway protocol. So it makes routing kind of easier and faster. Then we have routing tables. Now, routing tables, simply every host has a routing table. Every router has a routing table. What is simply that a routing table, all hosts or including router have a routing table that specifies to which network is it connected. For example, host A will tell you that, okay, I'm connected to this group of IP addresses, this group of networks. The same thing, a router will say, okay, I'm aware this network of this IP address is connected directly to me, or this one, I have the information and I know the path to it. And so that is simply what routing table consists of. Available IP addresses that are directly connected to them, available information about network addresses that are directly connected to them. And also, if it doesn't have, then there'll also be another IP that will be like universal. Like if you want to get to any other outside of the ones I know, this is another way to get out to that. So it's all hosts, all yes, all hosts, including router, all devices have what we know as a routing table within them. So using the information from the routing, the host now decides where to forward a particular packet or a particular data. Now to check for your own maybe device, especially the ones that do connect to the network, you can use in Unix only. I think Unix and in most Linux cases, if you type the command netstart, this program helps you to list out the available information within your routing table. So now this is an example of a routing table for a particular device, and then these are the list of available information within the routing table. Now, if you look at it, we have what we refer to as a destination. A destination is just destination of a network address that is aware of. So how to get there. And then we have what we refer to as a gateway. The gateway gives you the information about the IP address of the router that can forward packets to any other place outside of its own local connection. And then we have what we refer to as flags. It helps us to indicate, it helps indicate the different attributes for each route. Examples of such, when you have U, it simply means that route is up, is not down. So it means it's active. When you have G, that means that route is a gateway, like is a way out to the world. Yes. Then S simply helps you to know, okay, that letter S tells you that that route was configured statically. It wasn't dynamic. Every other one could be dynamic, but in this case, it is statically configured. Then we have REFs is known as references. So the number of active references to that particular route. So it's the numbers indicate the active references to it. Then the next one, use. It means number of counts or packet that has been sent using that particular interface. So looking at the image before us, that means for the default route, the number of packets that has used it is 1068 packets has used that route, that interface. Then if network interface, it tells you the network interface connected, the identity of network interface to that particular IP. Then the expire tells you, okay, for how long the address resolution protocol for that particular interface is valid. So in this case, is not. So that means it doesn't expire. It's as simple as that. So this is an example of how routing works from network A to another network 3 and to network A to network B and network C. So this when packets comes in, the router else sends it out to another router that then this next router is connected to network 3 and network 4. So depending on where the information is going, once it gets out through its gateway and hits this router, because of the information it has, this router, okay, I know about network 2, I know about network 3. So if machine 4 from network 1 needs to send information to network 3, and once that data gets through its own border gateway router, gets to the interface that is acting as a gateway for it, and if it's directly connected, it sends it to network 3. And then when it gets within network 3, the receiving router there sends it to the appropriate host that is aware of the needs it. So that's just simply how. Now the number of routers it travels through is what we refer to as the hops. The number of hops it takes to get to the particular host or receiver. So what are the key takeaways from this module 2 or from this unit that we just learned the routing? It says that routing occurs at network layer 3 of the OSI model. And in the case of TCP/IP, routing involves delivering packets to destination IP addresses to machines in other networks. Also, all hosts, including routers, now have a routing table that specifies to which network it is connected. Using information from the routing table, the host decides where to forward the packets. So each packet has a destination IP address at which the host will load. The host will go through each entry in the routing table and check if the packet destination matches that entry. Also, packet can be forwarded to hosts within the same network or to hosts on other network. And in this case, if it's going to another network, that means a router is actually needed for that. So that concludes our second live session for module 2, our second live session for this course. And in this second one, we have covered all the topics under module 2. So if you have any question, still you can always reach out through the discussion forum, or you can send it directly to me via my email address. And this will be addressed either during the next live session, or I will respond to you via the forum so that others too can learn from it. So once again, thank you, and do enjoy the rest of your day, the rest of your week. Thank you very much.